Welcome to multivariable calculus, the gradient. And when we think of a gradient, such as elevation, we think of a change, a rate of change. In mathematics, the gradient of a multivalued function is the rate of change in the coordinate system at a point. So we're looking at in each direction. The del operator operates on the function at a point to give orthogonal or perpendicular rates of change at that point. This is symbolized by the del operator upside down triangles. Del f of xy is the partial of f of xy with respect to x in the x direction, and that I is the unit vector in the x direction. Partial f of xy with respect to y, and this is the unit vector for the y direction. Now I'm going to prefer the bracket notation as much as possible, at least for the Cartesian problems. So we're going to look at an example. Two-dimensional gradient. Find the gradient of f of xy equals 3x squared, 3x y squared at 5, 7. Okay, well, this is going to be the x coordinate is going to be the derivative of x is 1. So 3 times 1 is 3. Y squared has been held as a constant to take the partial with respect to x. Now we hold the x constant and take the derivative. The partial is with respect to y is 2y. So we got 6xy. And then we can just plug a value in, and we have the gradient at that point. This being a nice, useful formula for where we can plug any point in, and this is just to give you a specific. The three-dimensional gradient is going to look like the two-dimensional, except it's going to have a third dimension, z. So we're going to find the gradient of f of xyz, or 4xy minus xz squared at, and here's a point 2, 1, 3. So the first thing we're going to have is the partial with respect to x of 4xy is 4y minus the partial with respect to x of xz squared is z squared. So it's 4y minus z squared. Then we're going to take the partial with respect to y. The partial of 4xy with respect to y is 4x. The partial of xz squared is taking the derivative of a constant, so that contributes nothing, that's a 0. And then we're going to have the partial with respect to z. There's no z in the 4xy term, so that's 0, minus x, which is now held as a constant, times 2z, so it's minus 2xz. Then we would plug our point in, and we would have a gradient at a point. So now we're going to also look at the del operator in cylindrical coordinates and find gradients in cylindrical coordinates. The del operator actually is more powerful than just finding gradients. We'll find divergence and curl. We'll get to those in another video, well, 2 other videos. In a cylindrical system, we're going to have a cylindrical coordinate system about the z-axis. Now the z-axis, if I had a cylinder like a wire, we would lie that wire in the z-axis. However the wire is oriented, that's well with the z-axis. Rho is the distance from the z-axis, how far out, and phi is a projection of an angle onto the XY plane, or the plane that's perpendicular to the Z. So we're going to have a little difference in finding our gradient. The gradient of f of rho phi z is the partial of f with respect to rho times the unit vector in how far out we are, the radius, 1 over rho, the partial of f with respect to phi, phi being the angle, and the partial of f with respect to z, or in our bracket notation, it's exactly the same thing, except we don't have the unit vectors explicitly shown. Now, why would we use cylindrical coordinates in science and physics or in engineering? Often we have things with symmetry of about a elongated direction, such as the magnitude of electrical field from a current conducting wire. So we would let the wire lie along the z direction, and we would measure out from there. A lot of times, the only thing we're interested in is how far out we go. In a lot of these fields that are fairly uniform, as we go in the z direction and as we go around with the angle, so we're more interested in the direction outward. But we need a way to do that, so it makes it a lot easier in dealing with x, y, and z if the action is the distance from an axis. So we're going to find the gradient of f of x, f of rho phi z is rho squared over 4 phi z hat, and here's a point. A lot of times there'll be no phi and z dependency, but that's, I'm going to show one sort of artificially here, just to example, find the gradient of f of rho phi z equals rho squared over 4 phi z at a point. The gradient of f of rho phi z is going to be the partial of f with respect to rho. It's 1 over rho, partial with respect to phi, plus partial with respect to z. And for this particular function, the partial f with respect to rho is going to be 2 rho over 4, or rho over 2. And then we treat the phi and z as constants. Then we take the rho square, but we have a rho in the denominator here. It's part of the formula. So it's rho over 4. And the derivative with respect to phi is going to give us, the z will be constant. The derivative with respect to phi is 1. And so then the derivative with respect to z, we're going to get the phi squared over 4, because there is no 1 over rho times phi. And so the derivative of z with respect to z is 1. And then we can simply plug our values of our function in and get our solution. Now, in the spherical coordinate system, we're going to have two angles. We're going to have a radius, or we're going to have an angle theta is the angle about the z-axis in the xy plane, and phi is the angle projection of the angle into the xy plane that we make with the z-axis. So del of f of 4 theta phi is going to be partial with respect to f, partial of f with respect to r, plus 1 over r, the partial of f with respect to phi, plus 1 over r sine theta, the partial of f with respect to phi. Or in bracket notation, now we use the spherical coordinates for things like gravitational fields, the magnitude of a gravitational field, or the magnitude of a point charge's electric field as we go out. And so a lot of times we're only interested in how far away from something we are, and we don't really care a whole lot about those angles. So this makes life a lot simpler than trying to deal with x, y, and z, and so on. So we're going to find the gradient of f of r theta phi equals r cubed, and we're going to have a point. Well, this is typical where phi and theta and phi are both zero, you don't care about, shall I say. So we're going to take the partial with respect to r, it's going to be 3r squared. The partial with respect to theta is 0. The partial with respect to the phi is also 0. And so we would get 3r squared, 0, 0. And we can plug in a point and get a value. And this is very typical. I forced the cylindrical coordinates to show you all three. This would be no real difference, except we have a divisor in the phi term. But aside from that extra divisor, this is not much difference. And this is more typical of what the point of going to the spherical coordinates is all about. We only care a lot of times, but how far out we go. Well, thank you for watching the video, and I hope you hit the subscribe button. There'll be additional videos. I plan to do one on the curl and one on the divergence when I get to Tom, which I'm assuming will be not that far in the future. So there's more to come. And we have a whole lot of other videos now already for you to enjoy and help you with your calculus.